Hello, I'm John Fitch, MIT science reporter. We're at MIT's Lincoln Laboratory in Lexington, Massachusetts, a major research organization which has played an important role in developing this nation's defense system since World War II. And although Lincoln Laboratory is perhaps best known for its work in radar and advanced warning systems, it has also seen the beginning of the computer era and has made many important contributions to it. To learn about some of its recent work in improving the relationship between man and this important machine, we talked with Professor Stephen Coons, an associate professor of mechanical engineering at MIT and co-director of the Computer-Aided Design Project.
John, we're going to show you a man actually talking to a computer in a way far different than it's ever been possible to do before.
Surely not with his voice.
No, he's going to be talking graphically. He's going to be drawing, and the computer is going to understand his drawings. And the man will be using a language, a graphical language that we call Skechpad, that started with Ivan Sutherland some years ago when he was busy working on his doctoral degree. And you will see a designer, effectively, solving a problem step by step, and he will not at the outset know precisely what his problem is, nor will he know exactly how to solve it. But little by little, he will begin to investigate ideas, and the computer and he will be in cooperation, in the fullest cooperation in this work.
Well, now, how does this differ from the way the computer has been used in the past to solve problems?
Well, the conventional way, the old way of solving problems with a computer has been to understand the problem very, very well indeed, and moreover to know at the very outset just exactly what steps are necessary to solve the problem. And so the computer has been, in a sense, nothing but a very elaborate calculating machine. But now we're making the computer be more like almost like a human assistant. And the computer will seem to have some intelligence. It doesn't really, only the intelligence that we put in it. But it will seem to have intelligence. In the old days, to solve a problem, it was necessary to write out in detail on a typewriter or in punch card form all of the steps, all of the ritual that it takes to solve a problem.
Because the computer is so literal-minded?
Because it's very literal-minded. If you, for example, in the old days, made so much as one mistake of a comma in the wrong place or a decimal point that was omitted, the entire program would hang up and wouldn't run. But nowadays, if you make a mistake, you can correct it, as you'll see, immediately, and the computer is much more tolerant and much more flexible.
We met next with Mr. Timothy Johnson of the Design Division of the Department of Mechanical Engineering and asked him to show us this computer and its Skechpad.
We're at the TX2 console at Lincoln Lab. This machine, a large computer, was built by Lincoln Lab in 1956 as a research machine.
Now, how does this differ from a computer that would be used to run your bank account or something like that?
Well, it's designed specifically for a study of manual intervention, where the man can command the computer to take different courses of action while the program is running. You can see we have several unusual pieces of input-output equipment here. We have a scope, a knob. These are unusual at the time, and push buttons, toggle switches. We have several other related devices. This made the TX2 a prime candidate for the Skechpad developments back in 1961, and it remained a program in this machine, so it would become a coherent partner in graphics, so the man can communicate with the machine.
Now, how do you actually go about communicating with a computer in a graphical sense?
Well, we are using an oscilloscope here, which is much like a TV set, except it's being driven by the computer. In order to get the information into the computer, we have to draw somehow on this display, and we use the light pen. Well, in order to construct a meaningful engineering drawing, we have to have several graphical manipulations. Ivan Sutherland's programs can draw straight lines and circles.
Well, that's about what you do in the drafting equipment anyway, isn't it?
That's a very good start.
T-squared.
In order to do this, we can position this bright spot in the middle of the cross that you notice at a desired location. And we press the button to command the computer to draw a line. It will draw a line from this position where I am now to any subsequent position of my light pin. This is much like a rubber band stuck on two pins. One is nailed on the screen here, and the other is at my light pin. So I can position this anywhere I want. Now, I lost tracking there. I moved the pin too fast, and that told the computer to stop drawing the line. Well, if you notice, that bright dot will jump onto the line as I get close to it.
Well, the dot in the center of the cross, when you get close to the line, jumps over onto it.
Correct.
Why does it do that?
It's much like a gravity field. At the end point, it is even a higher gravity field to allow us to position the point exactly on the line, or in this case, exactly at the end point. This allows me to move my pen quite coarsely, be sloppy while I'm drawing, and get a precision drawing out at the same time. So now I'm going to draw a second line.
Yeah.
And even a third one. Now, in an ordinary pencil and paper drawing, all we have is this particular picture. But the computer understands the geometry of the drawing here. What do I mean? I mean that if I point at this particular point and tell the computer to move that point by another push-button command, it will move not only that point, but all three lines that are attached to it.
And the delay between it's doing what you want it to is because it's computing all these changes.
That's correct. Now, if I made a mistake, I could delete my mistake by pointing at the line in question, for instance, and pressing the appropriate button. And it's gone. Now, I mentioned before we could draw circles also.
Right.
In order to do this, I must first indicate the center of my circle. Let's choose it to be here. And then I'll move out to an initial radius, let's say this point right here, and I press the second button to start drawing the circle. Here's our circle. Let me reduce the drawing slightly so our circle shows on the computer scope. And you see as I move the pen, it is ignoring the radial position. I've just gone off the scope screen here. The radial position of the pen and only looking at its angular position. So I can
be very sloppy as you like, in other words.
Right. In other words, the computer supplied the compass here, much like as it supplied the straight edge for the straight line.
If you go backwards, you erase it.
And I can wind it up the other way. Now, if I tell the computer to put that point right at this circle, right in that point right there, the computer knows that those must be connected. It turns out that they're not really connected. It's a very small nub there. Let me move this away and show you that they're really not connected.
I see.
But I have told it by terminating the point of the pen at that position that it must be connected. Now, I can tell the computer to satisfy this constraint command by bringing in a program under command of this toggle. And watch the scope. You see now that indeed the circle is ending at that line. We have constrained the drawing to behave this way.
Well, now, I wonder if you'd expand a little more on this idea of a constraint. Just what do you mean?
All right. Let me go to a second piece of paper. Now, what I've done here is I really saved away that drawing I just drew.
You can get it back again?
I can get it back, and I can select my drawing number by these toggles here. So I've selected a blank piece of paper, we'll call it. We have several pieces of paper. And I can, let's say I'm beginning to design. I have a very nebulous idea what I want to have in mind. And as I draw my part, let's say on the scope, it reinforces what I have in mind. This is, in general, part of the design process. And as I apply design criteria, stresses, and so on, eventually I will know what the exact shape of this part is. I shouldn't be required to draw the exact shape at the beginning. I really don't know what it is. But let's say I've decided eventually in this model that I want these to be horizontal and vertical, a box. I can apply a new constraint, a horizontal constraint here, and a vertical constraint here, and a horizontal here by pointing at the line and pressing a button. Well, now nothing has happened yet because remember I still must tickle that toggle over there to command the computer to satisfy these constraints.
I see. It won't actually let those rubber bands relax then until you say so.
Right. And I'll do that and watch again. There we have a box.
Well, now, this idea of having constraints like this, being able to make lines meet or to make them horizontal or vertical, makes it quite a step ahead of something that's just a drafting machine that allows you to draw, doesn't it?
Exactly. In other words, you can get the topology down of the part, and at any subsequent position in your design, you can make it to behave exactly what you want. Straighten the drawing up. In other words, you don't have to draw exactly at the beginning like you have to do in drafting. This is, of course, just one aspect of the program. Now, what I can do, in addition to this, is call up copies of master pictures. Remember that picture we drew before? I think it looks something like that.
That's right.
What I've done is I regard that first picture as a master. And I call up a copy of it, and I can manipulate it locally. I can reduce it, magnify it, I can rotate it, and let me place it right there. And I can do this several times. This is, of course, very instrumental for repetitive drawings like circuit diagrams or bridge bays, where we have several repetitive structures.
Oh, if you were drawing a circuit diagram, you might have little resistors or transistors or something already drawn and stored away, and you could call up as many of those as you wanted.
Right. Now, imagine that when I was doing my design work, I made a mistake in my master. Well, in order to correct that mistake, I would go back, and let's say I don't really want this circular segment to be in here. I erase it. Now I have the problem of making these changes to all the occurrences of this copy in my working drawing. This is very tedious nowadays. With pencil and paper, we have to remember where all the changes are. Now you notice, you remember the drawing, that we now have lost our circular arcs.
So if the manufacturer, for instance, of some electronic part changed the design somewhere one of these years, you could just automatically change all the drawings in which it appeared.
Correct. Well, now I've showed you many of the basic graphical manipulations we have available.
Incidentally, I would like to ask you how big this piece of paper that you keep referring to is, and how many pieces of paper you have available to you.
Well, this scope, which measures about 7 inches on the side, we regard this as a window that we can move over our paper and enlarge the size of this window. We can imagine the computer has a fixed sheet of paper behind this window. Its scale is approximately 2 miles on the side.
2 miles?
Right. Let's look at that. I can reduce this drawing slightly. And let me call up a copy of that master drawing again. Put it over the center there. Oops.
All right.
Now I've hit one stop already.
That's as small as you can. You're looking at the whole piece of paper, so.
Correct. And let me magnify it now. And now it's magnified so it's practically off the screen. Place another one in there.
Sort of like the picture within a picture within a picture idea.
Right, it's real nightmare material.
And as that gets smaller, even though the spot sort of disappears, it's really still there, isn't it?
Right, the computer has this all memorized in its memory.
But most of the things, though, that we live with in this world are three-dimensional rather than two-dimensional pictures like that. Is it possible to use a computer in that kind of problem?
Yes, we've expanded Ivan Sutherland's program into 3 dimensions. I have to bring that off the magnetic tape. There, we have that now. Here we have a single 3-dimensional object as seen from 4 separate views. We have a top view, as indicated by the T here, a front view, and a side view.
Oh, this is the way a mechanical drawing would be laid out, and together the other one is a perspective.
Right, with this addition. We can rotate this perspective separately from these 3 views. You get an idea of what we have here. Now begin to rotate it. You see it's rotating about an axis perpendicular imaginary floor. We have a wireframe object here with no fabric covering. Hence we see the rearward lines as they come in behind this S, which might be lying in the surface. So but there is no fabric here, so we see everything.
When the letters go around behind, they're backwards.
Right. Now, we are drawing much like we are in the 2-dimensional, except that is by moving a single point around with a light pen, but we're drawing directly in 3D. Here I have latched the pen onto the letter S. And as I move this around in the letter S, you see 4 dots moving in all the four views. This is the projection of the single dot.
In the side view, it's actually also following the S, but in the other two, you're sort of looking at the S on edge, so it's just moving back and forth.
Right, and this is because the S is indeed in the plane of that side surface. So we're seeing the single dot simultaneously in all four views as we're moving directly in 3 dimensions.
You're just tracking in that case. Can you actually draw something in all 3 dimensions simultaneously?
Let's put a roof on this object in this fashion. We'll latch onto that corner and we'll draw a pyramid.
I can see it from the side view. It's a false front house there.
Right. And I can also distort things, move things, like we can in 2 dimensions. If I latch onto this line here, or let's say this line over here, I can pull that out to the side and distort the object slightly. Now let's see what we've drawn here. We'll rotate the perspective, this view, again.
Quite a strange looking object.
And now we have a warped house under construction, perhaps.
And there's the F backwards in the perspective. Tell me, is it possible to do, other than these simple straight line shapes, for instance, curved shapes, could you design something like an automobile this way?
We're well underway with surfaces. We've begun the programming there, and we understand them, we think, pretty well.
To learn more about the handling of 3-dimensional objects in the computer, we met next with Dr. Lawrence Roberts of the staff of the MIT Lincoln Laboratory.
Well, you heard Tim Johnson explain how to construct solid objects with lines and wire figures. However, if we want to manipulate solid objects with the computer, we want to be able to represent their surfaces and so on as solid. Now here we have a representation of a piece of wood, perhaps, which is all of the lines of the sections behind each piece are hidden. As you'll see, as I start to rotate this object, the computer will place part of it behind the other part, and you will see that indeed the computer has a representation of it which knows that it's solid.
It's no longer just that wire frame. It really is solid, and when a line is behind the front surface, you just don't see it.
That's right. And so this is just one of my models that I can work with. I have a few others that I can call up. For instance, a wedge. I'll make the wedge slightly smaller and rotate it a little bit so you can see the properties of it. Now,
these fairly basic shapes.
Oh yes, you can construct quite a bit out of these basic shapes. As I move the wedge around in space, you'll see that it goes behind the solid and through it.
And the computer figures out where the lines should appear and where they shouldn't.
Where the intersection is.
You get the feeling of 3-dimensional space here very dramatically, as though this were a window and there's a fore area and a behind area.
Right. Now, as this comes out through the other object, you see that it indeed intersects it and can move right through it. Now, we also have been working with the flow charting of programs. To instruct a computer what to do, you need to write a program.
A flow chart then would be sort of a diagram of the steps that you'd want the computer to take in solving some particular problem?
Yes, in fact, I have a flow chart on here. This is with Skechpad again, and we have a demonstration of boxes representing statements to the computer to do some operation and compare some numbers and make a test and transfer one way or the other.
This is the way the human being would like to set it up, by drawing boxes like this that represent different computations.
This is the way that a programmer normally operates, and then he has to transcribe this to some form like cards or something as an input. But here we go directly from him drawing the flow chart and stating what each piece is, putting the statements inside the boxes, to a compiled program which he may execute on the computer.
I see. Well, you've shown us how you can enter numbers, say, by a typewriter, and now we can draw things for the computer directly. Are there other ways that we'd like to be able to communicate with the computer?
Well, we've been investigating here at the lab speech recognition and handwriting recognition for enabling the person to communicate better in those ways with the computer. There are a lot of techniques which would be very useful when combined into a whole, and all of these techniques, including the graphical manipulation, will make it much easier in the future for the man to dynamically converse with a computer.
Well, thank you very much, Dr. Roberts. Today, we've been visiting the MIT Lincoln Laboratory to learn about the computer Skechpad. Our guests have been Professor Stephen Coons, Mr. Timothy Johnson, and Dr. Lawrence Roberts. I'm John Fitch, MIT science reporter.